Have you ever pondered the fundamental nature of the universe? Could everything boil down to tiny strings vibrating in multiple dimensions? Welcome to the fascinating world of string theory. Consider this: you, me, the Earth, the stars, even the seemingly empty void of space, all might be composed of incredibly tiny, vibrating strings of energy. This is the captivating premise of string theory, a theoretical framework that dares to reconcile two of the most groundbreaking theories in physics: quantum mechanics and general relativity. In the grand scheme of theoretical physics, string theory is a significant player. It's like a bridge, connecting the incredibly small world of quantum mechanics to the immensely large universe of general relativity. And it doesn't stop there. String theory opens a Pandora's box of possibilities, suggesting a universe far more complex and wondrous than we ever imagined. A universe of extra dimensions, supersymmetry, dualities, and so much more. Now let's delve deeper into the intriguing aspects of string theory. In our daily life, we experience 3 dimensions of space, but what if there were more dimensions hidden from us? In string theory, that's precisely the case. This theory postulates that there are actually 10 dimensions, 7 more than we're used to. You might wonder, if these extra dimensions exist, why can't we see or experience them? The answer lies in their size. These dimensions are thought to be compactified or curled up into spaces so small that they're beyond our perception. But despite being hidden, these extra dimensions play a crucial role in string theory. They provide the necessary environment for strings to vibrate in different modes, resulting in various types of particles we observe in nature. It's like playing a guitar, where each string can vibrate in different ways to create different notes. Extra dimensions might sound like science fiction, but in string theory, they're a crucial part of the story. Imagine a world where every particle has a superpartner. That's the essence of supersymmetry. This intriguing concept is one of the pillars in the realm of string theory. It suggests that for every particle we're familiar with, there exists a superpartner. A particle with similar properties but differing in a key aspect: its spin. Now let's introduce another player in this cosmic drama: superstrings. These aren't your everyday strings. They're objects of one-dimensional length, vibrating in numerous ways. The different vibrations give rise to different particles, providing a harmonious solution to the puzzle of particle diversity. Supersymmetry and superstrings go hand in hand. The principle of supersymmetry is fundamental in superstring theory, as it allows the strings to vibrate in ways that give rise to both bosons and fermions, the 2 types of particles we see in the universe. In essence, supersymmetry and superstrings provide a new lens to look at the universe. Duality in string theory is about different perspectives leading to the same reality. Let's delve into the fascinating world of dualities. Think of it as looking at an object through different lenses, each revealing unique aspects, yet it remains the same object. In the context of string theory, we find 2 intriguing forms of duality: T-duality and S-duality. T-duality suggests that a string moving in a compact dimension of a certain size is identical to a string moving in a dimension of the reciprocal size. It's a bit like saying a tiny circle and a vast circle are the same thing from different perspectives. Then we have S-duality, which proposes that a strong interaction in one string theory can appear as a weak interaction in a dual string theory. It's as if the roles of the bully and the nerd in a schoolyard brawl can swap depending on who's watching. Duality is like a magic trick, revealing the deep connections between seemingly different things. Gravity, the force that keeps us grounded, has a quantum side too. String theory, with its unique perspective, offers a compelling approach to understanding this quantum aspect of gravity. Imagine the universe as a symphony of tiny, vibrating strings. These strings, according to string theory, are the fundamental constituents of matter and the forces of nature, including gravity. But gravity has always been a tough nut to crack, especially when we try to reconcile it with quantum mechanics. Here's where string theory shines. It elegantly brings together quantum mechanics and gravity, something that has eluded physicists for decades. This is achieved through the concept of quantum gravity, where the gravitational force is quantized just like the other fundamental forces. This marriage of gravity and quantum mechanics, through the lens of string theory, provides a promising framework to explore the mysteries of black holes, the early universe, and perhaps even the nature of time and space itself. Quantum gravity, through the lens of string theory, is an exciting frontier in theoretical physics. Like any scientific theory, string theory has its share of challenges and critics. It's a theory that's as complex as it is intriguing, and it's not without its share of controversy. Some critics argue that it's too abstract, too detached from observable reality. Others point out the lack of empirical evidence, as the energies required to directly test string theory are currently beyond our reach. There are also debates within the scientific community itself. Some believe that the multiple versions of string theory complicate rather than simplify our understanding of the universe. Others argue that the existence of extra dimensions, a cornerstone of string theory, is yet to be proven. But amidst these challenges, the future of string theory glimmers with promise. It continues to evolve and adapt, pushing the boundaries of our understanding. It is a theory that refuses to be confined, that dares to explore the uncharted territories of the cosmos. Despite the challenges, the quest for understanding the universe at its most fundamental level continues, with string theory being a key player in this journey. You might wonder, what's the use of string theory in the real world? Let's dive into it. At first glance, string theory with its extra dimensions and superstrings might seem far removed from our everyday reality. But surprisingly, it has potential practical applications that could revolutionize fields such as physics, mathematics, and even technology. Take the field of physics, for example. The development of string theory has led to new mathematical tools and concepts that are now being used to understand phenomena in the quantum world. This theoretical groundwork is crucial for advancements in quantum computing, a technology that promises to dramatically increase computational power. In mathematics, the influence of string theory is already evident. It has inspired new areas of mathematics and resolved long-standing problems. For instance, it has led to the discovery of mirror symmetry, a phenomenon that has reshaped our understanding of geometry. In the realm of technology, while the applications of string theory may not be directly apparent, they are nonetheless profound. It's like the development of quantum mechanics in the early 20th century. Back then, no one could have predicted that it would lead to the invention of lasers and semiconductors, technologies that are now integral parts of our daily lives. In a similar vein, string theory could potentially lead to technological breakthroughs that we cannot yet fathom. It might pave the way for new energy sources, advanced materials, or even innovative methods of space travel. The possibilities are virtually limitless. But remember, these applications are not guaranteed. The truth is, we are still in the early stages of understanding string theory. It's a bit like trying to predict the internet in the age of the telegraph. We can't foresee all the implications, but we know it's a game changer. So, string theory is not just a theoretical endeavor, it could have profound implications impacting our daily lives. So, we've journeyed through the intriguing world of string theory. We began by introducing string theory, an ambitious framework seeking to unify all of physics into a single, coherent theory. We delved into the concept of extra dimensions, beyond the familiar three-dimensional space we experience, and explored how these dimensions are integral to string theory. We then moved on to supersymmetry and superstrings, where we broached the idea that every particle has a superpartner, doubling the particle zoo in the process. We also touched on the concept of duality, including T-duality and S-duality, showing how these dualities provide different perspectives on the same physical phenomena. We then ventured into the terrain of quantum gravity, where string theory shines by offering a possible solution to the incompatibility between quantum mechanics and general relativity. The theory also presents a unique way to understand gravity, integrating it with other fundamental forces. We explored the world of superstrings in more depth, discussing their types and characteristics. We also touched on bosonic string theory, a simplified version dealing with particles devoid of charge, and the concept of open and closed strings. We highlighted how string theory connects with particle physics in the quest for a unified theory, and how it influences our understanding of cosmology, including the Big Bang and the expansion of the universe. We also discussed the intriguing idea of the multiverse, and the role of string theory in understanding quantum mechanics. Of course, we didn't shy away from the challenges and criticisms faced by string theory. Despite its elegance and promise, string theory is yet to provide testable predictions, a fundamental requirement for any scientific theory. But the journey is far from over, and the future is filled with exciting prospects. Lastly, we pondered on the potential practical applications of string theory in fields like physics, mathematics, and technology. Though largely theoretical, string theory could still revolutionize our understanding of the universe and inspire new technological advancements. Next time you gaze at the stars, remember, you might be looking at a symphony of tiny strings playing the music of the cosmos.